Hello, welcome to another module in this massive open online course. So we are looking at the classification of signals, various types of signals, and let us continue our discussion on this. Let us look at a different classification of signals, that is analog and digital signals. So what we want to look at now is basically analog and digital signals. So analog signals are basically continuous time signals, correct? These are continuous time signals which can take all possible values over a continuous interval. Okay, so an analog signal this is a continuous time signal xt, correct? It is a continuous time signal xt xt which can take values, that is it belongs to a comma b, that is it can take values, or let's say can take any value belonging to an interval alright, it can take values over a continuous interval. Okay, so such a signal, which is a continuous time signal, is termed as an analog signal. For instance, we have several examples of analog signals. A classic example is again sine 2 pi fct, correct? For instance, we can have sine 2 pi ft, which is a sinusoidal signal, which is, needless to say, this is an analog signal, and it takes all values that belong to the interval 0 to 1, or rather minus 1 to 1. Okay, so it can take all values belonging to the interval minus 1 to 1. For instance, another such analog signal, another example. So this is one example. Another such example is your, correct, so sine t, so sine 2 pi ft, it belongs to, can take values, all values belonging to minus 1 to 1, correct? And another such example is e to the power of t, which can take all values belonging to, well, basically e to the power of t, it can take all positive values. So basically from t equal to minus infinity to infinity, this can take all values basically from 0 to infinity. Of course, at t equal to minus infinity, as t tends to minus infinity, this tends to 0, and e to the power of t, it looks something like this. Of course, all of you are familiar with e to the power of t, that looks something like this. At t equal to 0, this is equal to 1, and as t tends to infinity, it tends to infinity. As t tends to minus infinity, it tends to 0. So you can see it takes all values. So e to the power of t takes all values in the interval 0 to infinity. It's a continuous time signal and takes all values in 0 to takes all values in the interval 0 to infinity. Okay. And on the other hand, we have also a digital signal. A digital signal is a discrete time signal. A discrete time signal, which we have seen, is only defined as discrete time instance and can take only values that belong to a discrete set. In addition to being a discrete time signal, a digital signal takes values only belonging to a finite, that is, it can take only one of a possible finite set of values. Okay. So, a digital signal okay, this is a discrete signal or a discrete time signal xn, discrete time signal that can take values, that can take only a discrete set of values. Or basically a finite possible values are the possible values it can take are finite. For instance, if you can take, if you look at sine t, okay, it can take any sine 2 pi fct, it can take any value in -1 to 1. So, it can take values from a infinite. So, these are infinitely possible values. Okay. So, these are basically, it can take values from an infinite set. So, it is an infinitely possible values. However, a discrete signal can take a digital signal can take values only from a finite set, or discrete set of values, or basically it can take only a finite, its possible values the set of all possible values has to be, the size of the set of all possible values has to be finite. For instance, xn can either be a typical example is xn is either -1 or +1. For instance, if you have a discrete time signal xn such that xn is either -1, remember this is not an interval, that is xn either equal to so it can take only values from a discrete set, or it can take only a finite number of values, that is 2 possible values, can take only 2 possible values. Only one of 2 values, and this frequently occurs, for instance, in communication. This is termed as a binary phase shift keying system, where a transmitted digital symbol can either be -1 or +1. A voltage level can be -1 volts or +1 volts to indicate the information symbol 0 or 1. Okay. For instance, this occurs in digital communication. This is known as a digital constellation. So, this occurs, a classic example of this would be in a digital communication system. Okay. Okay. This is termed as a digital constellation and so on. Now, yet another classification of signals can be real and complex signals. Okay. Now, this is obvious, a real signal either continuous time or discrete time signal, if it belongs, if the values belong to the set of real numbers, that is, it can take only real values, it is termed as a real signal. Either can be either a continuous time signal or a discrete time signal. If it takes values belonging to the set of real numbers or set of real values. It can take, it's a real valued signal. Okay. Okay, belonging to the set of real numbers. This is termed as, such signals are termed as, that is signals that take values belonging to set of, belonging to the set of real, but these are termed as real, these are termed as real signals. On the other hand, for instance, and again examples are abundant. For instance, again you go back to the previous signals, that is sine 2 pi f t or e to the power of t. Both of these signals, these are, needless to say, these take only real values. So, these are real signals. On the other hand, if you look at other examples, such as for instance, on the other hand, if you take other signals such as x t or a discrete time signal x n, which can take values belonging to the set of complex numbers. So, this is the set of complex numbers. So, when these take, that is signals that take values belonging to the set of complex numbers, that take complex values, the signals that take values complex numbers, these are termed as complex signals. Okay. For instance, the classic example of a complex signal is x t equals e to the power of j 2 pi f t, which can also be written as cosine 2 pi f t plus j sine 2 pi f t, where j equals the imaginary number square root of minus 1. This is a complex number, correct? This is termed as a, also termed as a complex sinusoid. Okay, cosine j 2 pi f t plus j sine 2 pi f t. This is also termed as a, this is also termed as a complex sinusoid. These are, such signals are basically, needless to say, these are complex signals which are complex valued. We can take values belonging to the set of complex numbers. So, we have real signals or complex signals, and complex signals, although they do not occur in practice, in the sense that these are not, these do not exist in nature, there can be, they are very useful in the representation of signals. In fact, again, once again, if you go back to the analysis communication systems, all communication signals can be analyzed or represented as complex signals, right, assuming the in phase and quadrature components of a communication signal. So, complex signals have a great utility, have a significant utility in the analysis, right, in the study of signals, and also analysis, carrying out analysis in various areas, all right, to understand different concepts and carry out the analysis in various areas of electronics and communication engineering. All right. So, these are also an important class of, this also represents an important class of signals. Okay. And yet another important classification of signals is deterministic and random signals. This is another very important, that is deterministic deterministic and random signals. These can also be either continuous time or discrete time signals. A deterministic signal is completely specified. It is deterministic, as the English word implies. It is determined. This implies xt or xn, that is completely specified that is completely specified deterministically at any given time instant. Again, you go back and take the example. For instance, it is given by a formula. For instance, sine 2 pi f t e to the power of t. These are deterministic signals in the sense that at a given time instant t there is no ambiguity. They are completely specified by a certain formula. Given a time instant, one can exactly determine what is the signal. For instance, if you take a look at sine 2 pi f t, given a time instant, I can exactly determine, correct, time instant t exactly determines the signal. However, this is not the case in a random signal. In a random signal, as the name implies, is random in nature. It takes random values at various time instants. So, a random signal again either continuous time or discrete time takes random values at different time instants. So, this takes random values at different time instants. Takes random values at different time instants, hence it is not completely determined ahead of. For instance, example, x of n. So, let us say you are signaling the outcome of a coin toss experiment. So, if the outcome is a heads, it is signaled by +1. If the outcome is tails, it is signaled by a -1. Okay. So, signal xn equals +1 if outcome equals heads, or if outcome is heads equals -1 if outcome equals tails. So, at each, so this is basically representing a coin toss experiment. This represents a coin toss experiment. What this means is, if at every instant of time you are tossing a coin, if the outcome is a head, you are representing it by -1. If the outcome is a tail, you represent. If the outcome is a head, you are representing it by +1. If the outcome is a tail, you are representing it by a -1. And therefore, since the outcome of the coin toss experiment is random, the signal itself is random in nature. This is a discrete time random signal, right? A classic example of a continuous time random signal is noise. For instance, let us say you have t, correct, and some kind of a signal which looks like this. This is termed as noise, okay, which is random in nature. Observe that this is random in nature and it wreaks havoc and it causes a significant of interference, correct. This causes the noise basically interferes with the signal, the desired signal, the information bearing signal. So, noise sometimes also not considered as a signal, but by going by our definition. So, it is basically a random in nature. Random in nature, and it is fundamentally important to understand the properties and behavior of noise to characterize or analyze the behavior of several systems. So, as important as it is to understand the signal, because the noise limits the performance of a system, it is as important to also understand the properties and behavior of noise to completely characterize the performance and behavior of a system. So, I will leave it at that, because the analysis of noise is basically falls in the domain of the analysis of random signals, correct, and it is fundamentally important to understand noise to characterize, correct, to character and analyze behavior of systems. That is because noise limits the performance of systems, correct. That has to be something that is remembered. Noise limits the performance of systems. Noise limits the system performance, and it is fundamental importance in the analysis, performance analysis, characterization of the behavior of any system, any practical system, because noise is an inevitable component of the, whenever we analyze signal, there is also an underlying noise component that is present. Its power may be less or more, or it's the relative power level, its power level relative to the signal might be varying, but it is an underlying component, and it is fundamentally important to characterize this, the properties and behavior of noise to fully understand the behavior of the system. Okay. And for instance, one such, again going back to our example of communication systems, the behavior and analysis of noise is fundamentally important to characterize the performance, right, the quality of information transfer, the accuracy with which information can be transferred, for instance from a base station to the mobile that you are carrying, to analyze the quality, all right, to analyze the bit rate at which information, to analyze the quality with which the information, the accuracy with which the information or the information symbols can be received. It is very important to understand and characterize the noise properties of the system. Okay. So, it is important in the analysis of systems. Again, another characterization which comes in handy in several analysis is even and odd signals. An even signal, as most of you must be familiar, similar to an even function, is x t equals, satisfies x t equals x of minus t, or for a discrete time signal x n equals x of minus n. For instance, you have a classic example, that is your cosine 2 pi f c t. For instance, let me just draw it. So, this is your cosine 2 pi f c t, cosine 2 pi f c t. This is an example. You can see that cosine 2 pi f t equals cosine minus 2 pi f t, and this is an example of a classic example of an even signal. On the other hand, an odd signal is satisfies x t equals minus x of t or xn equals minus x of minus t or minus x of minus n. Okay. So, or I am sorry, x of minus t equals minus x of t. So, let me write it in a slightly different way. I think that will be much more. X of minus t equals minus of x of t, and x of minus n equals minus of x of n. I think that is a slightly better way to write the definition of an odd signal. And again, another classic example of an odd signal is x of t equals sine of 2 pi. Sine of 2 pi f t. For instance, you can see here, this is the sine signal, correct, sine of 2 pi f t, and you can see that basically this is an odd signal. For instance, you can clearly see here and here. For instance, this is the value where t equal to this is the value for pi by 2. So, t must be equal to 1 by 4 f, and this is the value correspondingly at minus 1 by 4 f, and you can see this is basically 1, and at minus 1 by 4 f it is minus 1. So, this satisfies basically sine of 2 pi f t equals minus of sine of minus 2 pi f t. So, this is basically this is a classic example of an odd signal. Again, comes in handy, this concept of even and odd signals comes in handy when analyzing the properties or the behavior of signals. Okay. So, an even signal has even symmetry, that is symmetric about 0, x of t is x of minus t. An odd signal has odd symmetry, that is x of minus t is minus of x of t. Okay. And another very important classification of signals is periodic versus aperiodic signals. So, we have periodic versus aperiodic signals. Periodic and aperiodic. So, periodic and aperiodic signal, if t is the period, okay. So, this is an important classification. Again, this is a very important classification. This is a very important classification. X t is periodic if there exists t or if there exists a time period t such that x of t plus t is equal to x of t. This holds for all t, not a particular t, for all t. That is, for instance, you take a look at this, that is, there exists a time period capital T such that if you look at x of t plus t, shift it, like look at x of t plus t at a shift of capital T, right, it is equal to x of t, and this is true for all t, this is true for all time. For instance, let us consider a periodic triangular wave, okay. So, this is 0, this is t, this is 2t, 3t, minus t, and so on. And you can see all the values, for instance, if you look at this particular value and if you look at t later, so these are all the same, that is for any t, that is if you look at values t apart, capital T apart, they are all the same, alright. So, for any small t, x of t plus x of t is equal to x of t plus capital T, where t is known as the period for all, and this holds for all time instants t, okay. Such a, for and a classic example again is the sine, correct. We all know that the sine is a periodic signal, sine 2 pi f t. You can see that this is equal to sine 2 pi f t plus the period here is going to be, well, the period here is going to be 1 over f, correct, which is equal to sine, or just let us just make it sine 2 pi t, sine 2 pi t. So, this is sine equals sine 2 pi t plus 1 is equal to sine 2 pi t plus 2 pi, sine of theta plus 2 pi is sine of theta. So, this is again equal to sine of 2 pi t, okay. So, this is a period of sine 2 pi t, t equal to 1, t equal to capital 1. Now, there is a notion of a fundamental time period. What is, for all periodic signals, there is a notion of what is known as a fundamental period. Now, what is the fundamental time period or the fundamental period? Now, first realize that if t is a period of the periodic signal, then mt is also a period, where m is any integer, is also a period. Correct? Yes or no? Because xt is also a period for any integer m. For any integer m, and the reason this is true, correct, for instance, we have x of t plus mt equals basically x of t plus, so we will have x of t plus mt equals x of t, correct, and this also holds for all t, correct, because if it's periodic with t, then it's periodic with 2t as well. For instance, here you can see if you look at the point and 2t apart, it has to be identical. Okay. So, now therefore, the fundamental period is the smallest positive integer. Therefore, now fundamental period t is equal to the smallest positive integer equals smallest positive, well, it is the smallest positive, it's the smallest positive number, not integer, let us put it this way, it is the smallest time period. Is the smallest time period such that x of t plus t equals x of t holds for all t, such that this holds for all t. Holds for all t, for instance, and all other periods are basically multiples of this fundamental period. All other periods of this periodic signal are basically multiples of this fundamental period. So, all other periods all other time periods are multiples of your all other periods are multiple. For example, again let us go back to our example. Sin 2 pi t, you can show that t equal to 1 is a fundamental period, or t equal to 1 is a, for this signal t equal to 1 is a fundamental period. Okay. And therefore, it follows that any mt, for instance, such as any mt such as 2t, 3t, etc. Now, these are also periods, and in fact, for that matter also minus t, minus 2t and so on, these are also valid periods, because x of sin of t, for instance 2t, for instance here t equal to 1. So, 2, 3, minus 1, minus 2, etc. are also periods, because sin of 2 pi t minus 1 or sin of 2 pi t plus 2 is also equal to sin of t. Okay. So, any multiple of the fundamental period is also a period, and the fundamental period is the smallest possible duration, such that x plus t plus capital T, that is the fundamental period, equals x of t for all time instants. Okay. Now, the same can be defined for a discrete time signal. Again, for a discrete signal, discrete periodic signal, we must have x of n plus n equals x of n, and this must hold for all n. This must hold for all n, and this is basically your, this is known as the period of the discrete time signal. This is the period of the discrete time signal, and this is the smallest n for which this holds is known as the fundamental period. smallest n for which this holds equals the fundamental period n naught. Capital N naught. Okay, so that's basically periodic signals, continuous time periodic signals and discrete time periodic signals as well. Alright, so we have seen various classes of signals. Alright, starting with I mean there are several classes of signals such as deterministic and random, even and odd signals, and several different classes of signals. Alright, so you can go over these different classes and try to understand them better. Alright, so we'll stop here and continue with other aspects in the subsequent modules. Thank you very much.